The second problem, we're given the joint density function of x and y is b, and then we're given the dominant x squared and y squared is no bigger than 1, and density function is 0 otherwise. Question A, find b so that the above defined function is a valid joint probability distribution function. Yeah, so basically the same thing. We integrate this function in terms of x and y, and then we should get 1. So apparently x squared plus y squared no greater than 1 is an area of a circle with a radius of 1. And then it's really easy for us to calculate the area of it. Well, because b is a constant and it's a constant regarding x and y. So basically what we get is b times the square of the area of this circle. So we get b times pi equals 1. So b is 1 over pi. Problem B, we're asked to find expectation of x given y, expectations of x given random variable y, expectation of y, and so on. So first, we should let's look at expectation of x. So expectation of x is basically we move in the random variable x into the integral along with the density function of x. So first, actually, we need to know the marginal density function of x, which is to integrate this joint density function in terms of y. And here we have this, 2 over pi times square root 1 minus x squared. And then expectation of x is pretty much we add another x here, and then we integrate this whole thing in terms of x. So eventually we have this. And because inside here x and square root makes they make a odd function, so the final answer would be 0. So e of x is 0. And similarly, to get expectation of y, we get the marginal density function of y first, and then we have a very similar answer. Yeah, so expectation of y is also 0. The density function of x given y is defined as the density function of x and y over density function of y. So we get this result here, and the expectation of x given random variable y is to basically we move this x into this integral along with the marginal density, this conditional density function that we already have, and then we get an answer of 0. Same for y given x, 0. And x and y, we move random variable x and y. So for the expectation of x and y, we can get this also by calculating the expectation of xy given x. So we So this x would not be a random variable, but would be oh, actually, yeah. This is the random variable because if we calculate the expectation of all x, eventually we get xy here, like in the most inner layer, and we have 0 here because we get this. Expectation of y given x is 0, so to multiply x, we also get 0 eventually. And lastly, we're asked to prove or disapprove if x and y are uncorrelated. So it's pretty easy to see that expectation of random variable x, y is equal to expectation of x times expectation of y, because they're all 0. So we can say x and y are uncorrelated.